Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last lecture, we discussed about one application of angular momentum operator and the problem was particle in a ring. Today, we would extend our discussion to another problem which is particle in a sphere. There is a close relation between the two problems, that is particle in a ring and particle in a sphere, is that when you imagine that you are stacking a number of rings above each other, then you can imagine to construct a sphere in this way. And while the particle is in a ring, the particle's movement was restricted to one xy plane, where the z axis was non-operational, because for a fixed value of z, the particle was moving around the xy plane in a circular path. But on a particle in a sphere problem, not only the particle can go around the xy plane, that is particle in a ring, but now the particle can also move from one ring, so to speak, one ring to another ring. That means, in this case particle in a sphere, we have all three Cartesian axes x, y and z, all three are operational or active. So, now we would try to find the quantum mechanical solution of a particle of mass m, which is moving on a sphere of suppose radius r. To solve this problem quantum mechanically, we know we would start with by writing down the Hamiltonian of the system. So, the Hamiltonian would have two terms, one the kinetic energy operator, the potential energy operator, and just like the particle in a ring problem, we would make this, in this case the potential energy term is 0. That means, the particle while moving on the sphere does not experience any other interaction with any other particle. So, therefore, its Hamiltonian is completely given by the kinetic energy operator. Now, in this case, since the particle is moving around on a sphere, so all three Cartesian coordinates are operational. So, therefore, I write down the Hamiltonian as minus s square by 2m d square by dx square plus d square by dy square plus d square by dz square. So, please note here all the derivatives are partial derivative. That is because I have the particle is moving can move over all over the sphere. So, where x, y, z are variables will simultaneously get changed. So, this kinetic energy operator would have been just adequate if we were discussing particle in a cube or a cuboid. However, since we are discussing where the particle is moving on a sphere, so you would like to convert this kinetic energy operator from Cartesian coordinate to spherical coordinate. But before that, when we look at this term, there is a shorthand way to represent this, and this is called as del square. So, this is upside down delta or upside down triangle. So, this is given as either del, the symbol, or also known as nabla. This operator, remember this is actually an operator with second derivative with respect to x, y and z. So, this operator is known as Laplacian. So, Laplacian in Cartesian coordinates is simply given by this term. Now, what we would do is that we would recall how we defined our spherical coordinate. In spherical coordinates, we had x, y and z defined in terms of r, theta and phi variables. So, x, y, z are the Cartesian coordinates, r, theta and phi are the spherical coordinates. So, this is when I try to rewrite this Laplacian instead of Cartesian coordinate, when I try to write it in terms of spherical coordinate, this is what I would get. This long term, when you see, it has some second derivative with respect to r term, some derivative with respect to phi, some derivative differentiation with respect to theta. So, all three angular coordinates are present here. I can, when I look closely, I would see that the first term has only r terms in it, the second and third terms have all r, theta and phi. However, one important observation is that in the second and third term, this 1 over r square is simply multiplied here, and in both the terms I have 1 over r square. So, I can separate this 1 over r square and then I look at the terms which have only theta and phi dependence. When I look at this term which have only theta and phi dependence, I define a smaller name for this and I call this term as lambda square, or I call that as a Lagrangian. So, I have Laplacian which has x, which is defined in along x, y, z coordinates, and I can write this Laplacian in the spherical coordinates where r, theta and phi all are present. Additionally, I can define another operator, that is Lagrangian, which has only angular dependence. Note here, lambda square or the Lagrangian will have only differentiation with respect to phi or differentiation with respect to theta terms. So, 1 over r square lambda square is the second term and I have this first term. So, I simplified this Laplacian to this form. And I can now replace this Laplacian in my Hamiltonian over here, but before I do that, I look at the first term. The first term in this Laplacian in spherical coordinate suggests that I have to take a double differentiation with respect to r. What is r? R in this case is the radius of the sphere. Since my particle is going on a sphere, so therefore, I know what is the value of the radius of the sphere. So, therefore, for a problem r is constant, because I am defining that my particle is moving on a sphere of radius r. Since r in this problem is a constant, so therefore, this term, the first term in this Laplacian would not have any contribution. So, therefore, we can ignore this term. When we ignore that, we are left with this second term alone, and we will use this to define our Hamiltonian, which is now minus h square divided by 2m, and now Laplacian is given by 1 over r square and Lagrangian, or I can simplify this as h square divided by 2I, where I is m r square, the moment of inertia, Laplacian, Lagrangian. So, this is how the Hamiltonian is now defined in terms of Lagrangian. So, just to remind you, so I started with my Hamiltonian where I had kinetic energy and potential energy operator. I said that the particle on a sphere does not experience any external potential. So, therefore, V is 0 and my Hamiltonian has only kinetic energy operator, and I wrote down the kinetic energy term operator in Cartesian coordinate. I introduced something called Laplacian operator, and Laplacian operator when I express in terms of spherical coordinate, I say there is a radial term and then there is Lagrangian. So, the radial term is inactive here because I am talking about a sphere of a fixed radius. So, therefore, I am left with only the Lagrangian term in this. So, at the end I have defined my Hamiltonian in terms of the Lagrangian. What advantage do I get here? The nice thing about this Lagrangian operator is that if you compare this Lagrangian operator to another operator that we have introduced, that is L square operator, then you would see that L square is simply minus h bar square and Lagrangian. So, you would see that L square is minus h bar square and multiplied by the Lagrangian. So, therefore, if I rewrite my Hamiltonian now, instead of using the Lagrangian minus h bar square, I simply have L square. So, now you see what I have achieved is that I have expressed my Hamiltonian in terms of L square operator and a constant, because for a given problem mass of the particle is known, radius of the sphere is known. So, therefore, 2I is a constant. So, my Hamiltonian operator is expressed in terms of square of angular momentum operator, L square operator. What advantage do I have here? The advantage that I get here is that since I have spent some time in discussing what are the eigenfunctions and eigenvalues of this L square operator, now the Hamiltonian is simply L square operator multiplied by a constant. So, therefore, the eigenfunction of L square operator are also going to be the eigenfunction of Hamiltonian. So, remember we are trying to find out the solution of this Hamiltonian, that is the H psi equals E psi. We are interested in looking for the eigenfunction and the eigenvalues corresponding to this Hamiltonian, but now we see that this Hamiltonian can be expressed in terms of L square operator, and we know L square operator and its eigenfunctions. What are its eigenfunctions? Its eigenfunctions are the well known spherical harmonics, where I have psi L m, and you see they depend on theta and phi coordinate, and the eigenvalue corresponding to the spherical harmonics for L square operator is simply L into L plus 1 h bar square So, I know the eigenfunctions of L square operator, and now I would use this relation in the Schrodinger equation for the Hamiltonian operator. So, in place of Hamiltonian, I have L square operator divided by 2I. So, psi L m are again the eigenfunction of Hamiltonian operator, because in this case you can see that I can use the eigenfunction of L square operator as the eigenfunction of Hamiltonian operator. So, when I look at here the right hand side, so now this is my Hamiltonian H psi E psi, where the energy is given here. So, here E, the energy, of course, since I have L or m dependence, this is my energy. You see the energy expression does not have explicit dependence on m, but I know for a given value of L I can have 2L plus 1 number of m values. This is the general solution that I got from the quantum mechanical solution of angular momentum operator. Now, these are now the energy of the particle on a sphere. What are the possible values of L? So, L can have values 0, 1, 2 and so on and so forth. When L is 0, you would see m has only one possible value, that is A 0 0, and since L is 0, the lowest energy is 0, and this is 0 point energy. Like particle in a ring, the particle in a sphere also has the lowest energy or 0 point energy as 0. This would again indicate that the particle is at a rest or it is not moving when it is at the lowest energy level, or that is the 0 point energy level. The next one will be when L is 1. In that case, that I can have 3 different values of m. So, there can be plus 1 or minus 1 or 0. So, in that case the energy, since if I put L is 1, so I simply have 2 h square divided by 2I, and this will be threefold degenerate. Similarly, when I put L is 2, E 2, for L equals 2, I have 5 different values of m from minus 2 to plus 2 in the step of 1, and when L is 2, I have 6 h square divided by 2I, and this energy level will be 5-fold degenerate. So, in particle in a ring problem, we saw that except for the lowest energy level, that is the 0 point energy level whose energy was 0, all other eigenfunctions were 2-fold degenerate. That means 2 eigenfunctions would have same eigenvalue. for all non-zero value of m. In this case, in particle and a sphere problem, we see that the lowest energy again has has energy of 0, that means the 0 point energy is 0 in in particle and a sphere, but all other higher energies would have energy levels would have different levels of degeneracy. The second level has 3-fold degeneracy, the third level has 5-fold degeneracy. This is because the Hamiltonian can be expressed in terms of L square, and now in this by expressing the Hamiltonian in terms of L square, we could use the eigenfunctions and the eigenvalues of L square operator as the eigenfunction and eigenvalues of the Hamiltonian operator. So, this way the solution of particle and a sphere became very easy. That is because we have already invested a lot of time in discussing the solution of angular momentum operator L square. So far, all our systems that we have discussed, whether it is particle in a box or a harmonic oscillator or a particle in a ring or particle in a sphere, we have always discussed one particle. But we know in molecular systems that we would be interested in chemistry, we would have more than one particle to worry about. So, now we would extend our discussion from one particle to two particle system, and in that case how the quantum mechanical solution changes, that will be the topic of our discussion next. We would now discuss the internal motion of a two body system. Suppose I define a two body system with mass m1 and mass m2. Mass m1 occupies the Cartesian space of x1, y1, z1, m2 occupies the space x2, y2, z2. I can define the position of this mass 1 and mass 2 in terms of two position vectors r1 and r2, and the vector connecting mass 1 and mass 2 is defined by this another displacement vector r. I can define my r vector as from simple vector algebra as r2 vector minus r1 vector. So, therefore, the position vector of corresponding to this r vector is given by this relation, where x1, x2, x1, y1, z1 and x2, y2, z2 are the Cartesian coordinates of mass 1 and mass 2. When I have two masses m1 and m2 here, I can always define the center of mass of this two body problem. Suppose I have the center of mass of this m1 m2 two body problem is situated at this place, and I can define a position vector of corresponding to that center of mass with a capital R. Here this capital R vector is given by in terms of the masses of the two systems and also their displacement position vectors r1 and r2. This is general definition that we have obtained from normal vector algebra analysis. So, we have now this r vector, which is the position vector of the center of mass of the system, where r is given in terms of m1, m2 and r1 and r2. That makes sense, because if I change the mass of the two particles, the center of mass would change. If I change the position of the two particles, the center of mass would change. So, therefore, the center of mass should actually depend on m1, m2 and r1, r2. The individual Cartesian coordinates of this center of mass can be given in terms of these relations. They are very similar to the overall the vector representation that is shown here. Alternatively, what we have now, if you see that I started defining my problem in terms of two bodies with two vectors r1 and r2. Now, I have defined other two vectors, capital R and small r. The capital R is the position vector corresponding to the center of mass of the system, and the small r vector is actually the distance between the m1 and m2, the vector representing the distance between m1 and m2. So, what I have done is that I have expressed r1 vector and r2 vector instead in terms of the capital R vector and small r vector. So, I started defining R1 vector, I started defining the system, the two body system in terms of R1 and R2, and now I know that I can define this R1 and R2 in terms of this capital R and small r. So, I have two different ways of describing the system, one in terms of R1 and R2, another is small r and capital R. No matter how I define my system, I can always write down the corresponding kinetic energy of the system in these two ways. The first line shows the kinetic energy of the system, where half m1 v1 square, half m2 v2 square. So, r1 dot simply indicates the time derivative of the position vector corresponding for particle m1. So, this is the sum of the two kinetic energy of the two particles of mass m1 and m2. Alternatively, I can define now the kinetic energy of the system. Instead of using m1 and m2, r1 and r2, I have defined two different terms. One term is with respect to the capital R. So, this is time derivative of the center of mass, and this is the time derivative of the internal distance between the two masses m1 m2, where the capital M is simply m1 plus m2 and the small the mu is the reduced mass of the system given by m1 m2 divided by m1 plus m2. So, now there are two different ways of expressing my kinetic energy. The advantage of the second approach is that I can now see that in the first line, I see that the movement of the system is defined by two vectors, which are r1 and r2, but on the second line I see that I have expressed this kinetic energy operator in terms of two variables, which actually can be separated. How? Because the first term represents an overall translational motion of the center of mass, whereas the second term talks about the internal motion of this two body system. The internal motion of the two body system will be reflected by this small r when the distance of the two masses, for example, when they change. So, this small r indicates the internal motion of the system, which can be when the particle is when the two body is rotating or when the two body is vibrating. On the other hand, the first term represents the overall translational motion of this two body system. So, I can separate this two body problem to one body problem, where the first one body problem is essentially the translational motion of the center of translational motion of a fictitious particle of mass m1 plus m2 at the center of mass of the system, and the second problem is the internal motion. The second problem has this kinetic energy term, and suppose I introduce some external potential that would influence the rotation or the vibration of this two body system. In that case, that term, the potential term, can be incorporated into the Hamiltonian, like you have kinetic energy and the potential energy, and overall I can solve the Schrodinger equation. Translational motion and the internal motion can be solved separately. I need not worry about this translational motion, because if you look carefully, this resembles the particle in a box type of problem. So, I know its solution. So, I would be more interested in solving the problem like this. The application of this discussion is that when we have two body system, I can decouple this two body system into two effective one body problems. One is the overall translational motion of the center of mass, the other is the internal motion. I would ignore the overall translational motion and focus on the internal motion, and this is what we are going to do for the next problem, that is rigid rotor. Rigid rotor is defined as a two body problem, where the masses of the two masses are actually fixed in their the distance between m1 and m2 is fixed. This is a rotor which can go rotate, but while rotating it is not allowed to change its internal motion r. So, the distance is frozen. So, for such a system I can write down the Hamiltonian. So, I would like to solve this problem quantum mechanically. So, I have the Hamiltonian as T plus V, again the kinetic energy operator plus the potential energy operator, and I would say that again I would assume that there exists no external potential. So, therefore, the Hamiltonian is simply the kinetic energy operator, and in this case the kinetic energy operator can be defined as where this is, I know this is Laplacian. Now, you see I am using the reduced mass because I am talking about the internal motion of the problem. So, I have this Laplacian here, and I know, if you remember, I have the Laplacian which can be expressed in terms of a radial term and a Lagrangian term. We just discussed this, and in this case to the first term, the radial term has the differentiation with respect to r, but since we have defined that our rigid rotor is rigid, that means the distance between the length of this body is not going to change. So, therefore, this term will not contribute. So, I can ignore this. So, like the particle in on a sphere problem, I have this where I replaced my Laplacian in terms of the Lagrangian, and I can simplify this by using minus L bar squared Lagrangian as L square divided by, sorry, this minus H square H bar square Lagrangian is L square. So, this minus sign is not there, and I define it as 2I. So, now my Hamiltonian is again expressed in terms of L square, and I would be immediately able to solve this problem because I know the solution of this problem. I know the solution of the L square operator, they are the spherical harmonics. So, therefore, Hamiltonian will also have the same spherical harmonics as the solution. So, where these are spherical harmonics, please note instead of using L, conventionally one uses J. So, I am so that you are familiar with this notation, where the energy is simply H square divided by 2I J into J plus 1, and this H square by 2I, H bar is a constant, 2I is a constant for the problem, and we give this as a small name, and we call that it is a rotational constant, and it depends on the mass of the particle, mass of the reduced mass of the system, and the length of the rigid rotor, and J goes from 0 to 1 to 2, 0, 1, 2, and so on and so forth. So, in this way we can actually get the energy levels of the rigid rotor. So, again if I use J as 0, the energy is 0. When J is 1, I have 2B as the energy. When J is 2, E2 is 2 into 3, 6B, and so on and so forth. So, this way we also obtain the eigenvalues of the rigid rotor problem. So, in today's lecture we looked at two different applications of angular momentum operator. We saw particle in a sphere and rigid rotor. In both cases, when we wanted to solve this problem quantum mechanically, we reduced the problem, the Hamiltonian, to the L square operator, and we used the eigenfunction of L square operator and the eigenvalues of the L square operator to define the energy levels of particle in a sphere as well as rigid rotor. We would come back to this rigid rotor solution when we are discussing the rotational spectroscopy in molecules. Thank you for your attention.